these 2 minutes to leave, not to talk. Right? Talking is still not allowed. Okay, so linked lists. So we have been discussing abstraction data types a lot, right? And we said just yesterday that list is one example of an abstraction data type. Good? And we said you can implement them using multiple data structures, what we call data structures. Maybe the term is new for you, but we said you can implement a list, which is an abstraction data type, using multiple data structures. We give an example of an array, which is a possible way to implement a list. And this is the one that is commonly known. And we also have linked lists that can implement lists, right? The difference between list and linked list is huge, right? List is the abstraction data type. It's the way you abstract the organization of the values in one thing, in one collection, right? On the other hand, a linked list is a way to implement this ADT. So it's a data structure. When we say data structure, then you are thinking in a certain implementation. Now you should be working on lab, or you are already done with it. So when I say an implementation of a linked list, or when I say a word linked list, the first thing that comes to your mind is you have a node, and then you have another node, and then you have a link from this node to the other node, right? So every node has a pointer or a reference and a value, right? And this is why it's called linked list. You have links between different entities in this list or different nodes. Good? So a linked list is the data structure that implements the list ADT. Good? Today we are going to cover this. So what is a linked list? A linked list consists, as I said, it consists of a sequence of nodes. As you see here, you have a node, a node, a node, a node, and then what is inside a node doesn't really matter, right? And why this is important, why it doesn't really matter what is inside a node? Because you can store anything here. Remember, for example, for arrays, you can store elements that are integer, double, float, or even structures in C, or classes or objects in Java, right? Or even a pointer to another class or another array. So you can store whatever you would like to do inside one entry of an array. Exactly the same thing in a linked list. The value of the node, the thing that you store here, can be anything, right? And that's very important, because you can build on top of that multiple things that, as you will see later, and as you will see in more details into SI. Right? And then, in addition to the value that we don't care about which type of this value is right now, we also have a reference to the next node. Good? You have a value. These are our values for now. You can say these are characters or strings. And then you have a link to a node that is next to you. Here is one important difference between linked lists and arrays. Given, and maybe it's actually better to talk about this from the C point of view, the pointer point of view. And I'll touch on what is the difference between Java and C in this perspective. But let's talk about pointers, because this is what we know very well, I assume. So this you can think of as a pointer to another place in memory. And you can have a pointer to anywhere in memory, right? We know this from C. So this pointer that you have its value stored in one place, and the value that it points to stored in another place, do these two places have to be contiguous in memory? No, right? You can have an int A, then you create another pointer that points to A, but the pointer itself is stored completely in a different place, right? So the pointer and the value that it points to, they are not necessarily contiguous in memory. So having this as something that is a chain doesn't mean that they are stored contiguously in memory. So this node can be in one DRAM bank or one cache set, and this can be in a completely different bank, completely different address in memory, right? And that's a very flexible thing. So this is one flexibility and one kind of result of the way you implement the list using linked lists that does not exist in arrays. Yesterday, we saw some of the advantages and disadvantages of this. We said having the array contiguous in memory provides you with a faster access for any element, right? But it's harder to insert or delete. On the other hand, here we will see that it's very easy to insert or delete, but to traverse to a certain list, you don't have this address. So let me put it in a different way. Assume that this is an array. Good? Just purely array. If you know the index of this one, which means you know the address of this one because we know that the array name is the address of the first element. You can access the 10th element using your knowledge about the first element, right? The first element have the address of A for an array A. The 10th element has the address of, how can I access the 10th element in an array? A10, right? A and then 10 is the index of the array, gives you the address of the element number 10 in the array A. That's simple, right? But if I know the address of this node, it's not directly known what is the address of this node. You have to go through these hops, you have to go through these pointers one by one until you go there, right? Because there is no direct relationship. This makes sense? Yeah. You mean you have different types of values inside a node. This is a generalization, but people usually don't do this, right? Usually you have a linked list of just certain type. Why? Because it makes it much easier to create a node, delete a node, but generally you can write your own class that has, each node has a different type, it's up to you, right? But what is the use case? This is what is important, right? Is there any question here? Okay. So now we have this pointer, let's call it a link, because pointer is not in Java, and we will see now what really implements this link in Java. Good. So we have a link between each node and its next node. And then what about the last one? The last one doesn't have a next. Or if you want to traverse a linked list, how can you know that you reach the last element? Then you have to point to a null, right? So this is very similar to how strings are dealt with in C, right? We didn't have a type string. Then we said we are going to represent them using array of character, where the last element of this array is a null, right? So it's a kind of similar terminology here that null concludes your list. Good. The other important thing is generally a list can have a header or a head, or it may not have a head. What do we mean by head? The last element in a list, and this is a terminology that is good to know. The last element in a list is called tail, right? And the first element in a list is called head. You may need to have a head, and in fact, most linked lists have a head, but it's not necessarily, right? If you don't need a head to traverse your list, that's okay, right? But what do we need? If I want to have access to this linked list, what is the minimum knowledge that I need to know about this list? Or maybe let me put the question another way. Why you think we may need a head? Yeah. Exactly, to have a way to access this list. What if I don't have a head or any other pointer to any element in the list? How can I access this list? There is no way. You don't know. It's not like array, you have the array name and then you can access it. The array name again is a pointer to the first element, which is equivalent here to the head, right? If you don't have a head, you don't have a way to access, or in general, any pointer to the list, because maybe in the exam, for example, I tell you, assume you don't have a head, you have a pointer to a certain element, another element in the linked list. How can you traverse, right? So having a head is necessary to make sure that it gives you, it's the door or the access to this linked list. Then with the head, once you have the pointer to this one, it's very easy to traverse other ones because you have a next, a next, a next, a next, a next. Make sense? Is there any question here? Yeah. When we say a header, we mean a header to the full list. There is only one header or one head. It's not that each node has a head, right? So each node has a value and a pointer to the next one. Done. This is a node. A list is a set of nodes, and it can have a head, which is the address or a reference or a link or a pointer to the first element, right? So the head is usually here, right? This is the head that we are talking about. Make sense? You are saying the last one doesn't have a next. This is what I'm saying, is if you don't have a header and you don't have any other address of any other node, then you don't have access to this list. Why I'm saying this, why I'm adding a statement to what you said, because if you don't have a header, but for example, you have the address to this node, then in fact you have access to all other nodes except this previous, right? Once you have the address of one of the nodes, you have access to all the nodes that are next to this node. Make sense? Yeah. How you create a list without a header? So you would, yeah, so let's talk about maybe the lab example. You created one node, and then how would I create a list? We will see right now, but let's take it abstractly. You create one node, and then you create another node. You make this one point to this one, then you create another node. In the process of doing so, you lost the reference of the first one. You didn't store it in a variable, right? By doing this, you just lost the head. So initially you have the head, right? Because you created the node itself, but in the process of creating other nodes, you lost access to the first one, unless you store it in another variable, which is the head. Good? Is there any other question here? Good? Okay, so another question may be, under which situation that if I don't have a head, but I have an address of another node, I still have access to all the nodes. So what I just said in 2 minutes ago is if you don't have this list, but you have an address of C, then you have access to C and D, but you don't have access to A and B, right, in the current list. But under which situation you think, if I have address of C, I still gain access to everything? Can someone think of a situation? Yeah? Exactly. If you have a doubly linked list. So why I have access, when I said why, if you have the access of the address of C, why you still have access to D? Because you have this pointer, right? You have the link to D. If you are in C, you can still access D. But if you have a similar pointer from C to B, then in fact you can access B as well, and then A on the other hand. Please give me your name afterwards. Okay? So if you have what we call doubly linked list, it's a special type of list where the node is not just a value and a link to the next, it's also a link to the previous. Then having the address of any node in the list is sufficient to access all the list. And in this case, maybe you don't need the head, the tail would be enough, or any address in between is enough. Good? Okay. So another terminology that people usually use in data structure is a node successor is the next of the node. So it's the node that the current node, if you are in a current node, we call this usually current. The one that you are pointing to, your next is your successor, right? And then your predecessor is the one that is before you, which means the one that is pointing to you. Good? So if you are in a current right now, you have, maybe I just use my pen. Or maybe just go back to the speaker. So let's take B. The successor of B is C, right? But the predecessor of B is A. It's because A is pointing and B is pointing to C, right? Regardless of whether you have this link backward or not, right? The first node has no predecessor. This is your head, and the last node has no successor, right? It just has a null. Then what is the length of a list? If you are writing a method or a function that calculates the length of a list, this is the number of nodes you have in the current list, right? A special case of a list is a list with 0 elements, right? What would be such list? How you would implement it? In fact, a null pointer or a null reference or a null object in Java, just a linked list as well, right? But just happen to be an empty list, right? It has no predecessor, no predecessor, and it has no value. A list may be empty, which contains no elements, as I just said. So one important topic to understand about this link here, the one that we have here. We called it link to give it like a generic name. And then we said you can implement this link in C using pointers, because this is what we know. And then if you remember in our first lecture, we said one important difference between the mindset of Java and C is in C you have direct access to memory. You can do operations on memory addresses, right? You have fine-grained control over defining memory, allocating memory, having references to memory using pointers. In Java, we don't have pointers, right? But we have something that is very equivalent. So how do you think we can implement this link here in Java? I guess 3 lectures ago, we kind of discussed the difference between what we call object and a reference to this object, right? We said a reference to an object is equivalent to the pointer to a certain memory place in C. So a reference in Java is equivalent to pointer in C. What is a reference? If you have a class student, the one that we have in our quiz, then you just say student, my student, which is a variable that you created as part of this class, right? By just saying student, my student, and without using the word new, you didn't create any object in memory yet, right? But you still have a reference of type student. We call this the reference, right? Remember when I had this, this figure? So I said, so assume, and we discussed this in inheritance as well. So let's say you have a parent class, it's called parent, then you create X as a parent class. And then you didn't, and then later you say new, parent. And then here you create another parent, Y, right? What is the difference between this, the first one and the second one? The first one, using the word new, you are creating a place in the memory, and then this is of type object, which is parent, right? And then you are making X as a reference to this object in memory. Good? Y, we didn't create any object yet. So we have a reference that is called Y, but it's not pointing to anything. If later I said Y equal X, what would happen? You are making this Y reference pointing to the object, right? So you can think of a reference in Java as the variable name or the instant of a certain class, right? You say like class name and then you create certain variable of this class. This is your reference that is equivalent to a pointer in C. Is that clear? Good? So in C and C++ pointers, we said this, and then in Java you have the reference, which is you don't have this fine-grained control of this reference. And again, this is because of the mindset in Java, you don't have the fine-grained control on the memory. In C, you can do math operations on pointers, and we had so many examples on that, right? In Java, you don't have this. You just have the reference name as a black box, as something you cannot change, right? You can make it point to somewhere, that's correct, by assigning it another object, but you cannot modify it. You cannot add something to it, right? We already covered this before of what you can do of a class. You can dereference it by making it pointing to null. You can copy it, the example that I just gave, y equal x, you copied x to y. Then you compare for equality, which means you can check whether x equal y or not. What does it mean? We had this before, and this is a question for a bonus mark. What does it mean to compare two references for equality? Is that allowed? Allowed. But okay, what does it mean? Yeah. But a class has no one value, right? You can have hundreds or millions of member variables of a class, right? Then how to compare these? It's not a value comparison, right? Yeah. They are pointing to the same memory location, exactly. So they are pointing to the same pointer. And we had, I guess, 4 or 5 examples on this, where we created 3 references And then we made 2 point to the same thing, but then a second one point to a different thing. We said the third one is not equivalent to the first 2, but the first 2 are both equivalent to each other, right? You will find this in lectures, I guess, when you start studying. Okay, creating references. So you have a reference, and then if you want to create an object, so this title is kind of a misleading. So you declare a reference, but you create an object, right? So you would say, maybe I would change the slide title to be creating objects, right? It's clearer if you say this in this way. You create object, but you declare a reference. Student 1 is a reference. And now you just declare the variable of the type student. But student 1 equal new student, then you created an object of type student, and you are making student 1 pointing into it. Right? So yeah, here a person, B equal new person, B is a reference, and then the object itself, which B is pointing to, is the object, right? Okay. So how, given this knowledge, how we would create a linked list? Let's say we want to create the linked list like that has these values, like 44, 97, 23, and 17. So the first thing you do is a node or a cell, right? You create a node or a cell. Has a value and a reference to the next one. It happens to be that the next reference to the next one is also of type node or cell, right? Because your next one is a node or a cell. So this is why here you make your cell class that has a value and a next reference to another type of cell, right? And then here this is just a constructor that takes a value and like the reference to the next one and initialize your own values, right? This is similar to the what we called SLL node, I guess, in lab, right? You guys, you had this given in lab. This is why you said you don't need any knowledge about linked lists to be able to do the lab, because you are given the core. You can deal with this as just a class. It doesn't really matter what is here, right? We give this a name, and we had one complete lecture on that. Cell next, right? What did we call this? What is this thing? What I'm doing here? You are creating an object, or like we're declaring a reference for a class, right? We had one lecture, one of the early lectures in Java, just for this topic. What did we call it? It's called class composition, right? It's one of our topics in Java. It's called class composition. This is the title of the lecture, right? Class composition means you declare a class inside another class, right? This can be the same class type. It doesn't really matter, right? This is what you all need to know about the lab. If you don't understand what is a linked list, it doesn't really matter, right? You're just creating an object to another class. Good? And then here it's like we are initializing. So this is outside the cell thing. You can think of this here. We are creating the linked list. So we're trying to create. We start from the last one, and then you can start by any order. It doesn't really matter, right? You create a list that has the value 17 and a null pointer. Why this is null? This is your last element, so it's pointing next to nothing, right? So it has to be null. Good. And then you start creating them one by one. 23 has to point to this one. That's why here you send temp as your next one. And it's okay that this is your temporary node that you keep moving, right? And then temp will be 97 and then also pointing to temp. And then the last one, which is your header, 44. And now if you have a header, you would say, let's call it head. You would say, or here we call it my list, it doesn't matter. Then you would say head equal. Oh, we just actually created this here on the same line. So you would do this using two. It doesn't matter. But what we do here is we do two things. This one is creating this node, right? And then it's taking the type of this node and making a reference to it, which is called my list here, right? Your my list here is the head, actually, right? You can call it head if you would like. You are making head pointing to this node, and by this you created a head, right? Is there any question? It's not automatically, right? You make them point to each other by using the same temp thing, right? This makes sense? So in the first one, so we created the last one first, right? So we have done this. Let's talk about this line. This is line 1. Line 1 creates this one, right? And making temp point to it. This is what we do here, right? And then line 2, by using this new cell something, is creating this node. But just this, which is the right-hand side of the line, is creating the object but without reference, right? Now you make them move it from here to here, right? Make sense? And then you create this one, and then you delete this object, and then re-reference it to another object. And we keep doing this, right? Make sense? Is there any question? Yes. Tim was the head? No, right? Tim was just this one. So that's a good question. So you see what I have done here? This is the first line, second line, third line. In the fourth line, you don't make Tim take the output of this object creation, right? So if you want Tim to be your head, you have to change this line to be similar to the other ones, Tim equal, and then the new thing, right? Because we didn't change the reference of, how many times we changed the reference of temp? Just 3 times. The first one, it was pointing to the tail. The second one is pointing here. The third one is pointing here. In the fourth one, we didn't change temp, right? We just created a new reference, which we called my list. Make sense? So the output of this, after the end of this like code, temp would be actually pointing to 97, right? Make sense? The head would be my list, right? Before this line, them was still pointing to, again, 97. Yeah, it's still that. Yeah, that's correct. Each time of this, it's the head. But now you created another one, and you made it the head, but you didn't change them. You definitely can. Yeah, you can for sure. That's a good ad. Yeah, you can. Is that clear? So if it's clear, I have a question for you. If I want to keep, now we have, for this, we created a linked list, and we have a head for the linked list. Assume I would like also to have a tail for the linked list. Again, most tails have a head and a tail. What should I change in this code? The bonus mark as well. This list has a head, right? But this code doesn't keep track of what is the last node, right? I don't have a pointer to the last node. Yeah? Would you raise your voice? I changed the null value. I cannot, right? The last node has to finish with a null because it points to nothing, right? If you change the null to some valid value, then that means this one is not your tail. The next one is your tail. So the tail has to finish with a null. It has to point to nothing, right? But what I want to do is to keep track of the last node, yep? But this is exactly what this line does, right? So I guess you guys are confused with what a tail means, right? You know that a head points to the first element, right? A tail points to the last element, right? So the tail value, tail dot value is 17, right? It's not null, right? So the tail is not what is next, no. The tail is the last node itself, which has a valid value, right? By doing this, I just solve it, yeah? Yeah, that's a valid point if you already have the list. So that's correct. But what I was asking about is when you create the list itself. How to keep track. What you're saying is you already have a list that it doesn't have a tail. How you can have a tail for it? That's still correct. You traverse the full list until you reach a point that points to null, and then this would be your tail. That's completely correct. Yeah, please give me your name afterwards. But what I'm saying is, when creating this code, when creating the list itself, yeah. Yeah, as simple as that. But then, if you just do this, only, and then you put tail, yeah, no, this is here the mistake, right? Now you are saying replacing temp with tail, right? Right? This is what you are saying? Replacing temp here with tail, but also replace here to be tail, tail. Is that correct? Oh, one time. So this one and this one. Ah, that's correct then. Yeah, thank you. So what your friend here is saying is, when you create the last one, which you know that this is your last element, instead of calling it temp and then lose track of temp, call it tail, and then later you make another variable that is called temp, and then make the temp point to the tail, right? Another simpler way, it's less efficient, but what you would say here is, after creating this one, and before updating temp, it's just simply say cell tail equal temp, right? That's it. Right? After the first line, temp is in fact the tail itself. So by creating a reference that you call tail equal temp, you just created a tail. At this point, at the first line, temp was really the head and the tail on the same time. And this is one important aspect that you need to understand. We have two special cases in linked lists. The first special case is an empty list. It has nothing. And in this case, the head and the tail are none, right? Don't exist. The second special case is you have a list with only one element, which means it's the head and the tail on the same time, right? Make sense? Yeah. Making new list, right? I'm making new element, right? It just happened that I call this my list because it's your head, right? So it's pointing as if it's pointing to the full list, right? Good? Okay. So how we do this in Java, right? What I just showed you is a kind of generic implementation. Let's say how we implement this in Java. So, and you guys already know this from lab. You have a class that you call single linked list, call it anything. Then it should have two things, right? Or in fact, three things, if you'd say, if you would like to create a head. You would create a head, which here we call first, and then this is your constructor. Initially, your list is empty, so your head is null, right? And then you have other methods that has, so the first thing is this list doesn't have a value, right? Would this be possible? Can I have a linked list that only have references or links and doesn't have values? What do you think? What's the point? That's a good question, but is that valid? First, let's say if it's valid or not, and then what is the point of doing that? Is that valid? Yeah, why? Not valid. Yeah. Yeah, so I guess what you are referring to is you cannot have an empty object, right? What you are saying, the object should have something inside it, but it already has something here, which is a reference to another thing, right? Right? So what you said is correct, but it does not apply to here. So your friend here is saying, and we said this before, you cannot have an empty class, right? The class should have something because you create an object of this class, then it should have at least one member variable such that you create a place for this class in memory, right? Good. And there are ways to do this, but forget about this for now. But this is not even our case, right? Our case is you have a class that has only links to the next nodes, but it doesn't have a value. So your linked list is just nodes that are pointing to each other, but each node doesn't have a value. Is that valid? Yes, valid. Why it's valid? Is it even like a necessary that you have every object pointing to different places in memory? No. Still okay, right? Point to itself, that's still okay, right? So you guys should use your minds or the information that you already know, right? This has nothing to do with linked lists at all. I'm asking the question in a way, but in fact, at the bottom line, the question is as simple as, can you create a class that has a reference object to another class only? Yes, why not, right? We have this from class composition. You can have, is there anything that is preventing you in Java to have a class with only one member? No. Is there anything in Java that is preventing you from having this member to be an object? No. And that's it, right? So it's not linked list. Again, a linked list is nothing other than a data structure in your mind, right? So Java language, the hardware doesn't know anything about data structures. Whether you call it linked list or you call it like banana, it doesn't really matter, right? The hardware is dealing with the rules of the language, right? Which is you have a class, it has to have one member, this member should be a valid member, that's it. So we humans abstract the information of these things. We have nodes in our mind and then point to each other. But for the language, it means nothing, right? Good? Okay. So this was the linked list itself, which has basically the member that is called node. But node is another class that has an element and then a successor to it. So what I was saying here is this is your first element, which is a node. And it doesn't say whether the object itself has a value or not, right? So when you define this object itself, you can create, this is your successor thing, but here it's the element which is the node element itself. You can have this or you cannot have this, it doesn't really matter, right? So again, the content of the node can be anything, including nothing, right? Except the reference to the next one, right? Okay. We are just here initializing a node by having the element. This element here happens to be an object. What is object? What is this object thing? This is the first time we see this way of writing code. So what is this object thing? Why it's a valid code? Yeah? Okay. Yep. Would you raise your voice? It's a class, yep. It's parent class. To what? Yeah, it's the parent class of everything in Java, right? So object is a class that we said before, it's the parent of everything. Any class you create in Java is a child of this class. So it's a valid class name, and we know that you can use class name as a data type. So a node element can be, in fact, an object of a class, right? Or a reference to another class, it doesn't really matter. Right? And then this is your successor, which is the link to your next node. Okay. Assume I want to create such a list. This is just one example implementation of what we just wrote, right? We already had the class SLL, so I want to use it. I call my list numerals, call it anything, doesn't matter. And then Here I start creating elements one by one. And this kind of one-line code is in fact creating the full list. And you need to think of how to understand it. We will conclude by this one, right? What I'm doing here, I know that a node needs a value and a link based on my definition in the past slide. I need a value and a link or a reference to the other node, right? But a reference to the other node is itself a node, right? Which also needs a value and a reference to the other node, right? So instead of defining the first example we had in creating a list, we defined 4 lines of code each time we created the node, and then we copied the pointer to the other one and kept doing this, right? Here, using 1 line of code, and this is actually not a good programming skill. Your code should be understandable, so you should refactor it. But this is to make sure, this is kind of an exam question that see whether you understand what is going on or not, right? How to interpret this? Here I'm creating my first node. I'm sending the value to be 1. And what is all of this? This is, so you can think, this is here up to here. This is the second parameter to the constructor of the first node, right? So everything here is actually a reference to a node, right? But I want a reference to the second node itself, right? So creating this thing here, I have 1, a reference to 2, a reference to 3, right? This reference to 2, which I need as my second parameter to the initialization of 1, is in fact can be considered as the head to this list, right? Make sense? Right? So here, this pointer or this reference is this thing between brackets. It has to have a value as well and a pointer. The value is 2, and the pointer is a node, which is the third one, right? Good? If you're confused by this, another way to look into it from last to beginning, right? The last line here, the last line here is creating node 3, and it's the last one, so it has to be a null, right? And then the result of this thing is a reference to node 3, right? Which I take as an input to the next of 2. And after creating 2, I take the result as a next to 1, right? Is there any question? Okay, let's conclude here and we continue next week.